Hi everyone. So this is the surface energy balance example. The one that I started to post yesterday, whatever, it doesn't matter. Here's the surface energy balance example. So you might want to take a moment to pause the video so that you can write down the question and my little diagram over here. So pause it. I'm going to keep talking. What I've said is at thermal equilibrium, find the surface temperature of a PV panel given that G is equal to, well, about 900 watts per square meter. So drawing diagrams really helps me out with doing energy balances because it helps me visualize where everything's going, what's coming in, what's going out. And when I say surface energy balance, that's exactly what I'm talking about, is what's coming in, what's coming out, and where does that leave us with some of the variables that depend on the energy coming in and out, namely in this problem, what is the temperature of this surface? So over here I've drawn the sun, and this is supposed to be a PV panel, and this is the ground. And you have G coming in from the sun, this is your radiance from the sun, and then you have the radiosity of the panel leaving on both sides. So the panel is able to radiate and reject radiative energy from the top and the bottom. There's no G coming in from the ground. We're neglecting that. That's way beyond the scope of this class. So this is a very simplified example of what we would call a radiative heat transfer energy balance. Anyway, I'll give you something like the optical properties of the surface. So the top and the bottom are going to be different. In all cases, the materials that you'll see on a photovoltaic panel, the material on the top and the bottom of the panel will be different materials. The top of the panel is typically like a silicon or a glass covered structure with the solar cells, so there's all kinds of crazy optical properties going on there, and the bottom is usually like a Tyvek material or something light to try and encourage less cooling, more cooling on the bottom and no absorption. But anyway, so the optical properties for the top, we have alpha, that's the absorptivity, is 0.9. The transmissivity is 0, so we don't want anything, nothing's going through. The reflectivity is 0.1 and the emissivity is 0.9. However, the emissivity of the panel on the bottom is different because it's a different material. And if you remember from the lecture, optical properties are a function of, it's a material property. So because it's a different material, it has a different optical property. Anyway, let's actually do the example now. So I've said at thermal equilibrium, which means that the net flux will be equal to 0. So if Q is the net radiative flux from this surface, and I'm saying it's at thermal equilibrium, which means this rate of flux is not changing, it's going to be equal to 0, okay? And if you recall from the example in class, or, well, I mean, it's weird to say that, right? But if you recall from the lecture notes, this Q is equal to G minus J in a very general sense, where this is the irradiance, okay, and this is in watts per square meter, and this is the radiosity of the surface in watts per square meter, okay? So if I follow my picture over here to kind of like flesh this out, this will look more like 0 equals the absorptivity of the panel on the top times the incoming irradiance G minus J panel top plus J panel bottom. All right, so this is kind of where we start. So get that written down, and I'm going to erase this because my board is tiny. So I've asked you for the surface temperature, and that equation that I just had written up there doesn't have temperature in it anywhere. So we need to expound on J, that radiosity term. If you recall, J, the radiosity, is expressed as the emissivity times the emissive power of a black body plus the transmissivity times some incoming radiation plus the reflectivity times some incoming radiation. So that is the general expression for radiosity. Now, if we specify it for our situation, I'm just going to write the whole equation now, so get ready. So we have 0 for the net flux is equal to alpha of the panel on the top times G, okay, minus J panel top is going to be the emissivity of the panel on the top. Now, if you remember, the emissive power of a black body given the Stefan-Boltzmann law is sigma T to the 4. So I'm going to substitute that. So we have the emissivity of the panel on top times sigma temperature of the panel to the 4th power, okay? And I'm going to point something out here. The transmissivity of 0 is 0. So I'm just going to go ahead and drop that term right now for this example. So then I'm just left with the reflectivity of the panel on the top times G coming in, right? Okay, and then plus the emissivity of the panel on the bottom times sigma T panel to the 4th. And that's it, because I'm actually going to neglect the ground, so there is no incoming G over here, so there's no reason for me to write another G for the situation on the bottom. So just to be super clear, so this is the net flux, and it's equal to 0 because we're at thermal equilibrium, okay? This right here is in, and this whole thing right here is what's going out. So this is a surface energy balance for this particular problem, okay? This is coming in right here. This is what's leaving the top, this JPT. So this whole term right here is J panel top, the radiosity of the panel on top. And this term right here is the radiosity of the panel on the bottom, okay? So if you really want to impress your friends and family, write this, because it's all Greek letters. Anyway, what did I ask for? The temperature of the PV panel, right? And we see that there is T panel to the 4th twice in this equation. So basically, I know the absorptivity of the panel on the top. I know G, because I was given that. I know the emissivity of the panel on the top. I know sigma, that's a constant, and in case you don't remember, that's the Stefan-Boltzmann constant. And it's equal to 5.67 times 10 to the minus 8 watts per square meter per Kelvin to the 4th. So I know sigma, I know the reflectivity of the panel on the top, and I know the emissivity of the panel on the bottom. So I just need to solve for T sub P, the temperature of the panel. So you need to do a little bit of algebra, which I'm not going to do. If you need help with algebra, let me know, or reach out to a tutor. But basically, if you solve for the temperature of the panel, given that equation that I just had up there, you'll get let me keep my notation consistent. Okay, this is my expression. Solving for the temperature of the panel, I get G times the difference between the absorptivity of the panel on the top minus the reflectivity of the panel on the top. And then sigma times the emissivity of the panel on the top plus the emissivity of the panel on the bottom, all raised to the 1/4 power, because we had that T to the 4. So if you write down this equation and box it, that's cool, but I will warn you that in the case on a homework or an exam where you have another surface energy balance problem, this will not hold true for a different scenario. This is specific to this particular setup, right? So you might have to do some algebra in the future. So if we solve for, so I know G, I know alpha, I know rho, I know emissivity of the panel top, I know emissivity of the panel bottom, I know sigma. If I do all that math, I get that the temperature of my panel is 320 Kelvin, which is about 48 degrees Celsius, which is about 118 degrees Fahrenheit. Nobody cares about Fahrenheit, but I put it in there just so we kind of have a feeling of what that means. So, given this incoming radiation on that surface with those optical properties, this is what the temperature of the panel would be. This isn't completely realistic because there are two other modes of heat transfer that we haven't even considered here, and another strong one is convective heat transfer, which would basically be like the wind blowing over the surface and cooling it down. But anyway, this actually isn't too far off from what we really see for PV panel temperatures under direct sunlight with, full sun. 48C is kind of on the cusp of starting to deal with reduced panel performance. Once you go above 60C, you'll start to see pretty diminished performance for PV cells. And that's kind of why I'm showing you this problem, because we care about the performance of the PV panel, because the performance of a PV panel depends on temperature strongly. So you might see a problem on the final exam that kind of steps you through all of this stuff, where I start out by saying what's the temperature of the surface, and then I may give you a performance curve for a particular PV cell that will say like, okay, this is your expected, efficiency rating when it's this temperature. So what power output can you expect given this irradiance? It's not going to be, 100%. It's some efficiency of that, and that efficiency goes down as temperature goes up. So anyway, if you have questions on this, more specific questions, please shoot them my way. I know this is a little bit deep. If this doesn't totally, jazz you up and you don't think it's that cool, don't worry, you'll get through it, you'll be over it. But in the case where you are planning to continue on into engineering in your career, if you go into mechanical, electrical, chemical engineering, material science, anything like that, this stuff will come up again, and it's a really cool background to have. And I think more people should know it. So anyway, see ya.